Well, rational functions are tricky. There's no doubt about it. And I was walking around helping a lot of people. First step in the textbook is the author suggests we factor, just like Central Washington's doing here on their exam, and then reduce the polynomial. So really this polynomial is going to look like, let me put that over here, going to look like 3 times x minus 3 all over x minus 4. Now the only place where this rational function is going to look different than this rational function is at x equals -1. So see, x cannot equal -1 because that would make my original function undefined. And so when we look down here a little bit lower in the problem, at -1 we have a hole, -1 comma 2.4. So I'm going to explain, where does this all come from? But first, maybe let's look back. What is the y-intercept? Well, that's where you just plug 0 in for x. So we could plug 0 in for x into this function or into this function. It doesn't really matter. But if we do, we get -9 over -4 when you plug 0 in. So let me kind of put that right over here. F of 0 equals -9 over -4, which comes out to be just 9/4, which is the same as 2.25. So you could have 0 comma 2.25 here, or 0 comma 9/4. I hope I'm making that clear. Now, the x-intercept is when the y value is 0. So the only thing that's going to make a fraction equal to 0 is when the numerator equals 0. Right? Like I went around, I explained that to a bunch of people. If you had no pieces of candy and you have 5 friends, your friends are each going to get no candy. Okay? If you have 5 pieces of candy but you have no friends, how many pieces of candy is each one of your friends going to get? This question doesn't even make sense. So it's undefined. Like you can't even answer the question because you don't have any friends, right? So you cannot have 0 in the denominator. You can have 0 in the numerator. That's what we want in this situation. So that's why you can see they're just setting the numerator equal to 0. And when it says right here, show your work, this is exactly what I'm looking for. Like, are you setting the numerator equal to 0 and then solving it? And then why can it not be equal to -1? Well, because those factors right there cancel out. So if you wait till you get down here to do that simplification, if you don't do this right out the gate, you might accidentally put down -1 as one of your x-intercepts, right? See, you notice how they don't have -1 comma 0 over here. All right, so I hope I'm making that clear. Where do vertical asymptotes come from? It comes from when the denominator equals 0. So this sucker right here is the denominator. Let me label that, denominator. That equals 0. Okay, then horizontal asymptotes are about end behavior. So you want to look for the highest powers in the numerator and the denominator, and you want to compare those two. So since the degree in the numerator is 2, the degree in the denominator is 2, the equal degrees mean that at very large numbers, like 10 billion squared divided by 10 billion squared, those two guys are going to kind of even each other out. The rate at which the numerator is growing and the denominator growing is kind of the same, except that the numerator is always just 3 times bigger than the denominator. So the horizontal asymptote is y equals 3. It's going to reach like 3 billion squared over 1 billion squared. You might be looking over here and going, well, that seems like that stuff would make a difference, but a billion squared is going to be a billion times bigger than 1 billion sitting right over here. And you might say, well, the 6 is still there. It's still like 6 billion compared to a billion billions. Just this guy is the one that's going to dominate these terms over here. So when the numerator and the denominator have the same degree, you divide the coefficients. That's where the horizontal asymptote is. So that's why they got y equals 3. And again, the vertical asymptote, super easy. Just set the denominator equal to 0, but pay attention to the hole. There's no vertical asymptote. at the hole. Now that brings me to this idea. You can have Desmos open the whole time. So it seems kind of crazy to like not be comparing what's going on in our work to what we see on Desmos, right? So notice I've got the simplified version here in blue, and it totally matches up with the red function, except Desmos does a really poor job of showing where the hole in the graph is. So we know that the hole is going to happen at -1. Let me just show you that it's undefined at -1, right? But on the g function, it's not undefined at -1. So we could put it into the g function -1, and that tells you what the y value is for the hole. So we could come down here and we could go, okay, I want to put a hole in the graph at -2.4 in the y direction. Oh, not negative, positive 2.4. And well, you might say it's not a hole yet. Well, let's hold down on the mouse on that spot and then make it a hole, okay? You see, you got to force Desmos into showing that there's a hole there. You got to know that information. It's not going to show it to you. And it'll cost you on the final exam if you don't do that kind of simplification and that demonstration of work up here, that you factor the numerator and the denominator, you look for common factors. If there are no common factors, there isn't a hole in the graph, right? All right, so that takes care of the horizontal asymptote, the vertical asymptote, and where the hole is. You gotta find that y value. Okay. Now find the domain of h of x. Well, let's just look at the graph here for a second. You can plot all values along here until you get to -1. Then you got to jump over -1, and then you can plot all values until you get to, where's our vertical asymptote at again? At x equals 4, right? So do you see how they're going from -infinity to -1, not including -1. Oh, but we also want the numbers, not including -1, over to 4, not including 4, and then 4 out to infinity, right? So knowing where the vertical asymptote is, super important. We got to kind of like jump over that vertical asymptote. We also have to like jump over the hole when you're listing out what the domain is. Okay, there's the domain. Now, how are you going to get a decent looking picture of this? Well, shoot, on our test when we did this, I wanted you to label where the vertical asymptote was. So put down x equals -4 right there. I wanted you to label where the horizontal asymptote is. Y equals 3, I think it was, right? And then I also want you to label where the the hole is. So that was at -1, 2.4. I'd also like you to list what the y-intercept is. What was the y-intercept again? Well, you could click right here. I think it was 9/4, right? 2 1/4. And then the x-intercept's at 3, 0. So, you know, you can confirm that you have the correct x-intercept using Desmos. Make sure you're showing the work though. So we got 0, 9/4 over there. I've labeled that. Now, hey, if you were like, remember on the test when we had a paper part and you had no technology that you could use, you had to figure out which way the function was going, you know? Well, remember we have a horizontal asymptote. Functions can cross the horizontal asymptote, so you're not guaranteed that the function's going to punch up through here. But when you look at where the y-intercept is and you look at where the x-intercept is, I mean, the function's decreasing here. Once it hits the x-axis and it goes through the x-axis, it's got to keep going down. It can't come back up, right? And you might say, well, how do you know it's going to do this? Well, let's pretend like you know you're going at it clean here. You're not looking at the key like I am. You might say, well, that's kind of cheating, Nelson. You're looking at the key. And you put down your y-intercept at 9/4, right? Okay, so that's 9/4 right there. And then you put your x-intercept at 3 over here. And you also know you have a hole over here at -1, 2.4, -1, 2.4. Look, we're going to get from that spot to that spot, and then we got to get over here to this spot, and we're going to punch through. And you also know that you got a vertical asymptote right here, right? So you know it's got to come down. It's got to keep going down. It can't go back up, right? Now, because let's see, where'd my work go? It's up here. Because the denominator is factored into x minus 4, x plus 1. Well, the x plus 1's cancel out. But the x minus 4 has a 1 power on it. That means that it's going to alternate. The function's going to go down on one side of the vertical asymptote and up on the other side. Do you remember that? How we put an arrow going down and then we put an arrow going up? If there was only a factor, like one of those factors. If there was two of the factors, like it was squared, then you would have both of them going down, knowing that this left side's going down. Now, since we know this side's going up and we got a vertical asymptote right here, I would just make it get real close to the vertical asymptote. We could do more investigating, like does it ever hit the vertical, the horizontal asymptote? Does it ever hit the horizontal asymptote? But I don't think we need to get into that right now. And then you just want to make your function get closer over here to the horizontal asymptote, right? I think, you know, graphing this is very, very doable without Desmos. But, I mean, it seems kind of crazy not to have Desmos open, you know, to confirm that you're doing the right thing. The hole is the only thing that could kind of throw you off. All right, I hope I'm making that clear. Thanks for watching my video.